Welcome to qnawire.
So in this question, we want to compare the amount of energy released per gram of fuel. In part A, we look at and when gas is released 1.3 times 10 to the 8th joule energy per gallon. And a gallon is 3.788 liter. And then the density is 737 kilogram per meter cube. And we want this quantity of energy in terms of joule per gram. So it's really just unit conversion. So for part A, let's do for each 1 gallon, the mass for each 1 gallon, the mass equals rho times V, 333 kilogram per meter cube times is 3.788 times 10 to the negative 3 meter cube. So this is 2.79 kilogram. Then we know that this of fuel will produce 1.3 times 10 to the 8th joule. So the amount of energy per mass is 1.3 times the amount of energy per gram. So we also need to convert kilogram to times 10 to the 9 times 10 to the 3rd grams. So this is 4.7 times 10 to the 4th joule per gram. This is the amount of energy per mass. For part B, which says during fission, a nucleus has about 200 MeV. So we want to express it in terms of also joule per gram. So let's first look at how many atoms are there in each gram. In each gram, we have 1.00 times 10 to the negative 3 kilogram. But because we have 230, that is the atomic number of the atom we're using, so each atom has a mass of 230 mass of protons. So if you mass of proton, you'll find that each kilogram has 2.55 times 10 to the 21, and each nucleus will release 200 energy. We can again do the unit conversion. 100 MeV of energy times to convert this energy to joule. So this is a converter from joule to MeV. And then negative 13. And then we have 2.55 times 10 to the 21. Okay. Yeah, so this is 2.5 times 21 is the amount of nuclear in, so we already have gram over here. And so this is per gram. So finally, we get this number of 8.2 times 10 to the 10th joule per gram of energy produced by mass. And then part C says, well, okay, let's look at the proton-proton chain that cause the fusion in our sun, and it can be summarized as 6 protons forming 1 nucleus and leaving 26.7 MeV. So we have 6 protons gives us 26.7 MeV. And again, we want to calculate the energy density of this case. So we have 26.7 MeV, and again we do the unit conversion into joule, and then we divide them 6 times the mass of proton. So this gives us 4.26 times 10 to the 11 joule per gram. Okay, so that is for part. Finally, we have part D. I'm going to write it in this order. So part A, B, C and part D. For part D, we are looking at the amount of energy produced by our sun. And so we say that our sun produces energy at a rate of 3.86 times 10 to the 26 watt. And assuming that mass of 1.99 times 10 to the 30 kilogram are all gasoline, true, and then we ask, well, how long would it last if this is actually everything's gasoline? So we found that gasoline produces energy at this rate, rate. So 1.99 times 10 to the 30 kilogram, 4.7 times 10 to the 7th joule per gram. Per kilogram. Because here we have per gram, so per kilogram we just change 10 to the 4th to become 10 to the 7th. So this is to say the entire sun is able to produce energy of 9.4 times 10 to the 34 joule. And then this is the amount of energy, and then it's produce rate of 3.86 times 10 to the 26 watt. So if we want to know the total amount of times that it can last, time equals energy over power. So the energy is 9.4 times 10 to the 34 joule. Power is 3.86 times 10 to the 26 watt. If we do this, we'll find the total time to be 2.4 times 10 to the 11th second, or 7,600 years. If our sun were actually made of gasoline, it will not be able to last very long. But we are glad that our sun is actually dominating the reaction that is in C, and we can see this is a more efficient way of producing energy. We can produce a lot more energy with the same amount of mass.